This video is going to be on converting equations between polar and rectangular form. So converting equations between polar and rectangular form. Alright, so we're going to recall some of the formulas, or not formulas, but substitutions we talked about previously. So x is the same as r cos theta, y is the same as r sine theta, r is the square root of x squared plus y squared, but it may also be helpful in this case to remember that r squared is the same as x squared plus y squared. And then theta is the same as tan inverse of y over x, or sometimes it might be helpful to think tan theta equals y over x. So we're going to be using these, just like we used to convert polar coordinates, we're going to use these to convert the polar equations. So when you're converting, there are basically three goals, or three steps that you should go through. So the first thing that you're going to do is make substitutions. The second thing that you're going to do is simplify what you have, because your end goal is a recognizable equation. And I'll show you more what I mean as we do some examples. So, if we are converting to rectangular, for our first example, we're going to consider r equals 4 as the polar equation. So if you can picture this, if I had r equals 4 and I'm looking at a polar grid, then that would be like, oh, the line or the curve that has a radius of 4, so I'd count out 1, 2, 3, 4, and it's like, oh yeah, radius 4, that should probably be a circle that's centered at 0, 0 with a radius of 4. So we there's some sort of like common sense or intuition that helps us kind of have an idea of what these answers should be. But if I wanted to do this by hand, I have right here that r equals this stuff. So I'm going to replace the r with the square root of x squared plus y squared, and I still have it equaling 4. So at this point I've made my substitution. Now I want to simplify, and I don't necessarily see anything that could be simplified here, but I know that my goal is a recognizable equation. So hopefully you can see if I get rid of this square root by squaring each side, I'm going to have x squared plus y squared equals 16, and now I recognize that equation. I'm like, oh yeah, that's definitely, that's a lot better focus. Oh, yeah, like, oh, that's a circle centered at 0, 0 with a radius of 4. So at this point, we have a recognizable equation. Here's another example. Let's say we have r equals 4 sine theta. So if I look at this one, I'm not quite sure at this moment what it's going to be. I don't really know how to look at a polar grid and think like, oh yeah, that's going to look like something. So right now that doesn't really help. But if I look up here, I know that I have a substitution for r. I've got all this stuff. And I've got a substitution for r sine theta, but I don't have a substitution for just plain old sine theta. So what might be helpful in this case is to take the entire equation and multiply it by r. So what happens when we do that is we get r squared equals 4r sine theta, and the reason I wrote it that way is because r sine theta is something that we have up here. And this works because r squared is one of the substitutions that we actually do have. So I'm going to replace the r squared with x squared plus y squared, and I'm going to leave the 4 because nothing changed about that, but the r sine theta becomes a y. And hopefully you're recognizing from what you know about conics that if we have an x squared and a y squared, then it either has to be an ellipse or a circle. And because these both have the same coefficient, this must be a circle. So for us to get this in standard form, because when you write that recognizable equation, I would like it to be in standard form, so it's like ready to graph. I think that's the most recognizable, as opposed to the general conic form where you just kind of make it equal 0 and then leave it like this. So I'm going to subtract the 4y over, and then I'm going to try to get this in the standard conic form, which means that I need to complete the square on this part right here so that I can basically see where the center of the circle is and what the radius would end up being. So negative 4 divided by 2 is negative 2. Negative 2 squared is 4. So I'm going to say plus 4 right there. That's what completes the square. Then I have to add 4 to the other side. So what that leaves me with, the x squared part didn't need to have the square completed on it. This part is going to be y minus 2 squared, and that equals 4. So at this point I can say that's a recognizable equation. It's a circle that is centered at 0, 2, and it has a radius of 2. Okay. Next, we could say theta equals pi fourths, and I've seen a couple times where these equations are theta equals something. To be honest, I don't see it very often, so we're going to practice a few of these, but for the most part, we'll see equations where it's in the form r equals. That's more common. You might be able to tell I've learned a lot about polar, but in some ways I still have some gaps. So I'm giving you guys the best of the information I have, but each year it gets a little bit better. So if you can picture this one, if I look at this on the polar grid, pi fourths would be this degree measure right here. So if I have the angle theta equals pi fourths, then it would make sense that at least this part of the line would be what it is. But if you think about it, this maybe should go all the way through, and so if we use theta equals pi fourths, that should probably be a linear equation. And if you look, this is a linear equation that would go through the origin at 0, 0. And because it's pi fourths, it should probably have a slope, it looks like it has a slope of 1. So I'm keeping that in mind as I write the equation because that could be helpful. So the things that I know up here is I can have theta equals tan inverse of y divided by x, or tan theta equals y divided by x. And I'm going to go ahead, I think technically you probably could use either of, well, you definitely could use either of these, but this one is going to be a little bit easier. So I'm just going to say if I do tangent of theta equals y over x, and my theta is pi fourths, then I'm really saying tangent of pi fourths equals y over x. And tangent of pi fourths would be root 2 over 2 divided by root 2 over 2. So I really get 1 equals y over x. So at this point I've made my substitutions, I've started to simplify a little bit, and now I'm going for that recognizable equation. So since I know this needs to be a straight line, it should probably be in like y equals mx plus b form. So I'm going to go ahead and multiply by x on each side. And so my rectangular equation here would be y equals x, and so it kind of makes sense. It's that straight line. It's got a slope of 1. It goes through the origin. Okay, and then one last polar equation to convert. R equals 5 over cos theta. So on this one, if I look at it the way it is now, I can kind of see that I've got a substitution for r, but I don't have a substitution for cos theta. If I try to do what I did in the other example and I multiply by r on each side, that would make this r squared, but on this side it would put the r up with the 5. It wouldn't put it with the cos theta, so that doesn't really help me. So what I'm going to do is I'm just going to try to get rid of this fraction. So I'm going to multiply by cos theta, and the reason that I did that is because now I have r cos theta equals 5. And I know that r cos theta is just x. X equals 5. So if you think about this, this is actually also a linear equation. This is a vertical line. So it's a vertical line that goes through 5. So we're done. Okay, so those are, of course, there are other ways you can, or not other ways, but other circumstances you can convert to rectangular, but I think this video is long enough as is. Okay, so next we're going to look at converting to polar. So for the first example, we're going to look at x squared plus y squared equals 25. So on this one, x squared plus y squared equals 25, I'm recognizing, oh, that's a circle with a center at 0 and a radius of 5. So what you should maybe be noticing is that we can use this equation like we did before. So I'm going to take the x squared plus y squared and turn that into an r squared instead. And this problem has a few approaches that you could take with it. I don't know necessarily the easiest way to think about this of solving for r, but in other problems it helps to make this equation equal 0 and kind of factor it. And so I'm going to go ahead and just show you guys using this method, and if I hear that there's a common way of doing it differently, then I'll let you know. So if we were to factor this, it'd be r minus 5 and r plus 5. And so this one would tell us that r equals 5. This one would tell us that r equals negative 5. So this one's saying we have a circle centered at 0 with a radius of 5. That kind of makes sense. Circle with a radius of negative 5 doesn't really make sense, although I guess if you think about it, a negative radius kind of goes backwards on the circle, so maybe it kind of does make sense. I don't know. Either way, this is the answer. So I've seen a couple different approaches. Either way, we know what the answer is supposed to be, so that's how we got there. I'll update you guys if I find more information on ones that are more simple like that. In this case, the more complicated ones I think are actually easier because they're less vague. So here's the next one. So I have, this is in general conic form, but again I can see the x squared and the y squared both have the same coefficient, so this must be a circle. So what I'm going to do here, and this is kind of, there's a trick to this, but I think if I show it to you, you'll be like, yeah, I could probably do that in the future as well. So if you look at this, what I did is I took out the coefficient of 2 because that put the x squared and the y squared right next to each other, because I know that x squared plus y squared is the same as r squared. So this is 2r squared. So that's one manipulation that's helpful to do. I know that I can replace the x with r cos theta, and I know I can replace the y with r sine theta. So next, and it's kind of like what we did before, what we're going to do is we're going to try to factor this problem. So if you notice, all of these have r's in them. So I'm going to take out a GCF of r, and that leaves me with 2r minus cos theta plus sine theta equals 0. And then what my goal would be is just like before, I take my factors and I set them equal to 0. So this r right here equals 0, and this answer is kind of trivial because if you consider r equals 0 on the polar graph, that'd be like a circle with the radius of 0. So that really is just saying the pole, that's that point right there in the middle. So basically, whatever this graph was, it must have gone through the pole. So this is often going to happen for us, and we can just kind of ignore that. It's not wrong, it just is kind of like, so who cares, it goes through the point 0, 0. So for this other one, I'm going to go ahead and say 2r minus cos theta plus sine theta equals 0. I'm going to move everything away from the r. So that would give me 2r equals positive cos theta minus sine theta. So I subtracted sine over, added cos over, and then I would divide by 2. So I'm going to say this equation is r equals cos theta minus sine theta over 2. Or if you wanted to say 1/2 cos theta minus 1/2 sine theta, that would be fine as well. I'd be okay with that. Alright, another example of this. Let's say we have a circle that's actually in standard form. we want it to be written out like this so that we can see where the x squareds and the y squareds and all of that stuff is. So what I'm going to do is I'm going to write this out twice so that I know to FOIL it, because a lot of us forget to do that. So when I FOIL this, I should get x squared minus 4x plus 4 plus y squared. And because I know that I'm going to be factoring this to solve for that r value, I'm going to go ahead and minus the 4 over to make this equal 0. And then I want to rearrange things so that I can start putting my r's in there. So these are going to cancel out because they're same number but opposite signs. So I have an x squared and a y squared I can put together because I know those have one replacement. And then I've got negative 4x also there. So I'm going to take this and replace it with r squared. And I'm going to keep the 4, but I'm going to replace the x with r cos theta. And then just like before, I'm going to factor this. So I'm taking out the GCF of r. That leaves me with r minus 4 cos theta. And again, just like before, this is r equals 0, and that's the pole, and that's kind of trivial, so I'm going to ignore that. And then over here, this one is pretty simple to solve this time. It's going to be r equals 4 cos theta. And so there's my equation for that one. So I know these are kind of weird, but we'll practice them, and I think you'll get the hang of it. So I hope maybe now you're seeing why I've factored this one, even though it seems kind of obvious. You could just be like, Ms. Rice, that should just be r equals 5. Anyway, okay, last one. Let's say we're considering the straight line y equals negative x. So on this one, anytime you have a problem like this where it goes through 0, 0, anytime we have a straight line that goes through 0, 0, then we should do the version where we have theta equals a degree measure, because those would go straight through. If this has been shifted up or down and it has a different y-intercept, we will not be able to do that. But if it goes through 0, 0, then we know that we're going to be able to write the line as an angle. So I need to have, if I look at my formulas here, I'm going to need to have y divided by x. So I'm going to go ahead and divide by x here. And the reason I'm doing that is because I know that y divided by x is the same as tan theta. So right now I have tan theta equals, and this would be negative 1. So if I want to solve for theta to get that degree measure, I'm going to do tan inverse. And tan inverse of negative 1, there's a few different ways to write it. So 3 pi fourths would be if you do tan inverse of negative 1 and you look in the second quadrant. You could also think of this as 7 pi fourths, because that's negative 1 in the fourth quadrant, and these two would be the same line. It's just two different ways of writing the same thing. You could also say 135 degrees or 315 degrees. Those are all exactly the same thing. So there would be a lot of different ways to write this one line.